Hope my screen is visible, right? Is my screen visible?
Yes, sir.
Okay. So, welcome to uh, the problem solving session of uh, for the week 5 of the course Geotechnical Engineering 1 offered by Professor D.N. Singh from IIT Bombay, and I am Yogendra Narayanan. I am a PMRF research scholar. So, to give a brief introduction of this about this problem solving sessions, these sessions are entitled to uh, make the learners familiar with the concepts of the particular week and solve the problems by solving problems from uh, various sources, and thereby uh, m- making the learners proficient in the content of that particular week there, and subsequently it will be helpful for the learners in approaching the NPTEL exams as well as the uh, other competitive exams in their in the future, and uh, ultimately help ultimately it will be helpful in their professional careers. So, to give a brief background of what was taught in week 5 is characterization of fine grained soils, especially determination of their index properties by introduction to and detailed discussion about consistency limits, how to determine them, what are all the inferences from those consistency limits, and followed by the concept of effective stress was introduced. So, uh, covering the all the aspects of this week 5 contents, we can enter into this. We can start this session. Uh, so today it will be it will be both some theoretical questions as well as numerical problems. So which I expect the attendees to uh, interact interact actively and solve them. So moving to the first question, Atterberg limit is important for classification of which type of soil? Atterberg limits are are important for classification of which type of soils?
Uh,
Option A
Fine,
coarse grained, option B fine grained, option C boulders, option D stones.
fine grained soil.
Yeah. So Atterberg's limits are invariantly it is for fine grained soils. So Atterberg's limits are classified as liquid limit, plastic limit, and shrinkage limit. So from this we get several indices from which we utilize them for further characterization. So the right option is fine grained soil. So coming to the next question, the minimum water content at which the soil remains in liquid state and minimal resistance to flow is the minimum water content at which the soil remains in liquid state and poses minimal resistance to flow is option A liquid limit, option
Liquid.
B plastic limit, option C liquidity index, option D shrinkage limit.
Option A.
So Option A. So if as per the definition of if we come to liquid limit, the definition is the minimum water content after which the soil starts to behave as a liquid. That is, it starts to flow. It is in a slurry state. So that is liquid limit. And plastic limit is such that it starts to uh, behave in a semi-solid manner. And uh, liquidity index uh, is the relative difference between the plastic limit and the liquid limit. And shrinkage limit is the border at which it exists in a completely saturated system. So, what is the shear strength of the soil at liquid limit? Any idea? So, we have seen that soil exists in a liquid-like state at uh, liquid limit. So, does it possess shear strength? I see somebody has written 0. Ideally, it is not 0. It has a very minimum shear strength. As per IS standards are considered liquid limit of soils at uh, sorry, the shear strength of soils at liquid limit is approximately 2.7 kPa, very minimum. So this is the general value for shear strength of the soils at liquid limit. You can note it down. So as far as this question is considered, as you rightly mentioned, it is liquid limit. Hope it is clear. Now moving to the next question. So which apparatus is employed for finding the liquid limit of the soil? Which apparatus is employed for finding the liquid limit of the soil? So it is Casa Grande apparatus. Automatic oven is for leach ateliers and leach ateliers apparatus is essentially for autoclaves and automatic oven is for drying. So Casa Grande apparatus is essentially used for uh, determining liquid limit. It consists of a semi, semi hemispherical bowl which is connected to a mechanism such that it can be rotated so that it goes up and down. It has a fall of 1 centimeter and the soil is filled and a groove is made, and at different uh, moisture contents the samples are prepared and a groove is made, and the system is uh, it is tapped repeatedly by and the number of blows for the groove to get closed is counted. So this is Casa Grande's apparatus. So as you rightly mentioned in the chat box, some of them are mentioned. It is Casa Grande's apparatus. Uh, do you have any idea of any other techniques used for measuring for determining liquid limit? One of the techniques, as one of the learners rightly mentioned, it is called phone penetration technique. So that is also one of the technique, but ideally universally uh, followed uh, tests for uh, determining liquid limit is Casa-Grande's apparatus. So the right option is option B. So next question. Any doubts or any clarification? So let us move to the next question. What will be the y-intercept obtained if the linearly increasing portion of the graph plotted between volume of sample V and water content W, that is plotted in liquid limit test, is extended to y-axis? What will be the y-intercept obtained if the linearly increasing portion, the graph plotted between volume of sample and water content in liquid limit test, is extended to the y-axis? Are you able to understand the question first? So now let us just draw the graph between volume of the soil sample and water content. Now what happens is, now let us come in the reverse manner. So let us once the water content start decreasing, so the total volume starts to decrease. That continues up to a certain point, which we term it as shrinkage limit, and in between we have plastic limit, and at any point we have liquid limit, and further it is a slurry. Now once it has achieved the shrinkage limit is the point at which the soil is exactly saturated. Now once if we start drying the sample to the water content lesser than shrinkage limits, what happens is that the volume the water that is present inside the pores, it starts drying up, but the total volume of the sample does not get affected. So beyond this, the graph will be extended like this. Now further decrease of moisture content, there will be no change in volume, and at zero moisture content, that is when the water is completely dried, that is not exactly possible. It has some minimum water content known as hygroscopic moisture content. So even that if it is dry, since shrinkage limit uh, to shrinkage limit it is air dried, and after that if you even if you oven dry it, and if the moisture content is completely zero, so in that case the total volume will be, so total volume is volume of solids plus volume of voids. Now what happens? Volume of voids, when you start decreasing from water content from shrinkage limit, it will be volume of water plus volume of air. So once it is completely when you are it is a partially saturated system, once we are decreasing it, and at this one it gives the entire volume of solids. So
Sir,
yes,
you have mentioned volume of the solid as the at y-axis entire volume. It is volume of solids and volume of voids.
yeah,
Extension, yeah, you have mentioned in the graph. You can look at, sir. It is not a volume of the solids. Sir. It is a dry volume.
yeah, dry volume. So that in the case it is dry volume of the sample completely. Hello?
Sir,
Yeah, yeah.
you have written just now in your y-axis volume of the solids. Sir. That is from where to where?
No, no, that is at the intercept.
At the intercept, it is not a volume of solids, sir. It is both the volume of solids and volume of voids, air voids. Both are there. You are not extended. You have shown as a horizontal line only. You have not extended. Extended line, extended straight
Yeah,
line.
yeah. So this will be yeah, yeah. Though
That is what
actually
I am
here
asking.
what happens is that that when you extend it, it will not uh, exactly become zero. So there will be a minimum point which is
Yeah,
actually
that is
volume of
actually
solid.
volume of the solid. That
Yeah, yeah,
portion is volume of
yeah,
solids.
yeah. Thank you for correcting it.
Yes,
So
sir. Thank you, sir. It's okay.
just make a correction in that. So it
You
will
can
be
you can erase it, sir. You can erase the volume of solids
yeah,
and
yeah.
you
I'll
can
do it.
y-axis.
Thank you for pointing out.
Yes, sir. It's okay, sir. Mm.
So when you
Small.
extend it, it will be volume of solids. So hope it is clear. So the answer is uh, C. Coming to the next question. Sorry, there is a change in question number. So please pardon the correction. So I can make it here. So which parameter can be found by calculating the slope of the graph depicted below? Which parameter can be found by calculating the slope of the graph depicted below? So this is the graph which is water content and logarithm of number of blows. N is number of blows. It is a liquid limit graph. N is number of blows. So when you calculate the slope, what we will get? Any idea? So now let us consider two cases, which is when we do it like this. So this is N1 and corresponding it is W1. Sorry, when we are coming like this, so number of blows, water content. Okay, let us move like this. N2 and W2. This is how we calculate the slope. That is N2 and N1 is obviously log. So now the slope is W2 minus W1 divided by log N2 minus N1. That is N2 minus log N1. So if you write this W2 minus
Sir,
W1.
excuse me, sir.
Yes, yes.
It is log n1 minus n2. N1 is bigger, you have written.
No, that is when we do it because the slope is negative here. So we will be according to, but the when how to put it? How can I say is that
As per your what you have written, as per that it should be n1 minus n2, I think.
yeah. So that is here N1 and
Ah,
N2,
yes,
which
sir.
will
That's all.
give log of
N1,
N1 by N2.
n2. Yes, sir.
So this will give you the slope which is termed as flow index IF. So this is flow index. So this is one of the important parameters which can be related to shear strength also, but not exactly. There is a uh, how to put it, direct relationship or proportionality with uh, shear strength. So this is flow index. Now question 6. After performing several tests on the soil, it was found that its plastic and liquid limits are 26% and 42% respectively. Calculate the plasticity index of the soil and determine its degree of plasticity. Is my screen visible?
Yes, sir.
Yeah. So plasticity index is defined as IP, liquid limit minus plastic limit. So now 42 minus 26, which will give us 16%. Right. So this option and this option is ruled out. Now, how to decide whether it is highly plastic or medium plastic? Any idea?
When IP is more than 40, I think it is highly plastic.
No,
Exactly, I am
not
not sure.
exactly. So if you compare if you refer the A-line chart, now we
Okay.
have IP 16%, and one more thing is liquid limit should be greater than 50%. So that also corresponds to high plastic condition. So since liquid limit is also lesser and IP is also in the range of in this we are getting 16%, so it will be medium plastic. So medium plastic range of liquid limit will be around 35 to 50%. 35, I'm not remember if I'm
Yes,
not
sir. 35 to 50. 35 to 50.
50%.
Yeah.
So that is the range of medium plasticity. So and one more thing is if you want to classify further based on whether it is a silt or a clay, so you have to calculate the theoretical uh, in plasticity index, which is uh, which will be given in the A-line chart. So there is a question based on that. So once it comes, we will be discussing that. So right now it is, you can remember that for it is the classification of plasticity is done usually by using liquid limit and plasticity index. All right. So this is the option here, right option, 16% and medium plastic. Medium plastic is because the liquid limit is not greater than 50%. Hope it is clear.
Yes, sir.
So moving to the next question. In a liquid limit test, the moisture content at 15 blows was 60% and at 35 blows was 150%. The liquid limit of the soil is. In a liquid limit test, the moisture content at 15 blows was 60% and at 35 blows was 150%. What is the liquid limit of the soil? So how do you define liquid limit corresponding to the blows and the initial moisture content?
The water content at 25 blows is normal liquid limit.
Yeah. So as far as this Casa Grande testing is considered, so liquid limit is the water content when, that is, water content of the sample when the groove closes at 25 blows. That cannot be exactly attained. That's why what we do is we uh, uh, conduct trials with several moisture contents and note down the blows, and then we uh, extrapolate it to get the curve, best fit curve, and from that we calculate the water content corresponding to 25 blows. So that is what, now it is a simply application of uh, slopes. So that is y2 minus y1 by x2 minus x1. So when you plot water content by log n, you will get a straight line. So now you know for 15 you need to get 25 blows. So for that you don't know what is the, this is 25 blows, this is 60 blows, and this is sorry, so water content is lesser, yeah, right,
Yeah.
it is 60 blows.
Sir, is the data is correct, sir? Because lesser blows, moisture content, is it correct?
Just a minute, just a minute. So 15 blows was, no, sorry, so you can exchange this.
Yes, sir.
So this you make it as 150. I think this is a type
Yeah.
mistake. So it is 60%. Now you check.
Now it is okay, sir.
So now it will
Fine.
be 150. And this is, so this will be, sorry. So water content is 150. For 150 it is 15 blows.
Sir, blows.
So for 35 blows it is 60%. You need this for 25 blows. 25 blows, what is the water content? Now what we will do is 150
I don't know. I
minus
made a mistake.
liquid limit by
15 blows.
log of
Yes, blows.
25 by 15 equal to liquid limit, or you can enter both entire value also. So 150 minus 60 by log of 35 by 15. How much we are getting? Because both the slopes are same, so you can either you can do it by this part and this part, as or otherwise you do it this part and entire part. So if you do it separately, you will get both sides WL. So which might be there might be some calculation difficulties. So can you let me know the answer?
Sir, I want to ask one thing.
Yeah,
That suppose these formulas and these calculations, uh, like log and sum,
just a minute, just a minute.
in
Yeah, tell me.
in the exam, some kind of scientific calculator may be allowed to do that. If in the actual exam these comes,
Yeah, it will be allowed, I think.
okay,
But I will confirm you and I will let you know. So I
yes,
think it will be allowed.
Sir, it is allowed, sir.
Yeah, yeah.
NPTEL virtual calculator is there. Same will be
Virtual.
allowed in GATE also.
Yeah. So that's what, because without this, they will not conduct the examinations. So most you don't know, you need not worry about this.
Can
okay,
I can I add something, sir, for his
Yeah.
question?
Yeah.
In some competitive exam, if they don't allow calculator, they will take complete log cycle rather than in between,
Yeah.
so that the denominator will be eliminated. Log 10 becomes 1.
Yeah.
That's also possible. Without calculator also we can do, but accordingly they will give the data.
Mm. So you can solve this. How much you are getting?
Option D, sir.
Yeah. So it will be around 114%. You can calculate it. So this you can take it entirely to this side, and it will be you will get a fraction, and this you can multiply it, and you can eventually subtract it from 150. So the answer will be 114. You can just make a change in this. So there has been a typing error. So please excuse me in this. Others, are you getting this? Or you are finding any difficulties? So let us move to the next question. If the slope of the graph plotted between water content versus number of blows is steeper for two soils, which are soil A and soil B, what can be inferred from this? So two soils are there for which water content, number of blows are plotted log. So for soil A you get a steeper graph, and for soil B you get a flat graph. So that is now here two conditions it should satisfy in order for us to compare the results. So one thing is, for the initial starting portion should be same, and final portion also is same, such that we can compare the slopes, or eventually we are going to compare the slopes, so that does not matter. So now what happens is that first soil A has, this is A and this is B. So now, as I discussed before, so the slope gives flow index, right? And the flow index is indirectly proportional to shear strength, right? Is it clear? You can switch off the mic. I think some noise is coming. So now, any doubts still there?
No, sir. It's okay.
Okay. So now, the corresponding thing is, so now soil A has more slope. So now if the slope is more, flow index is more, and therefore shear strength will be less compared to soil B. So shear strength of A is greater than shear strength of B, right? So we can, so this slope is gives the shear strength value alone, but what we have been presented is that soil A possesses a higher rate of shear strength reduction with water content compared to soil B, and soil A possesses a lesser rate of shear strength reduction with water content compared to soil B. So now what they are mentioning is that rate of shear strength reduction itself, which cannot be found out from the value of flow index. So the slope of this curve gives flow index, and the it cannot be directly compared, but if you consider it from a common point of view, let me just zoom in. So the rate of reduction, so as water content is the number of blows is uh, is decreasing at a larger rate compared to if you see at a particular water content.
Sir,
Yeah,
can I interrupt, sir?
yeah. Tell me.
Soil IF is more, sir.
Yeah, that's why shear strength of yes.
It
Okay.
should be less, no?
Yeah, soil
Yeah.
A shear strength is lesser.
Now it's okay.
Yeah. So now if we consider at a particular water content, the number of blows for soil B is more compared to number of blows at soil A. So ideally, if you take as far as only flow index is considered, you cannot quantify the rate of shear strength reduction. You can quantify the rate of reduction in water content with blows, or uh, ideally that can be the rate that you can quantify. So this question, why I have included, is that it gives a it poses a ambiguity. So you should be very careful in approaching this. So in this, actually the ideal answer is, as far as shear strength reduction is considered, no inference can be made. So you can quantify that from these graphs, that shear strength of A can be lesser than shear strength of B, but you cannot comment on the rate of shear strength reduction. So that is why the option would be option C. So you cannot comment on how shear strength is reducing with water content here. Moving to the next question. 6 and so moving to the next question. Boiling point of bound water is greater than that of free water. Select the true statement or statements. So it has a multi-correct option. Boiling point of bound water is greater than that of free water. Second option is freezing point of bound water is lesser than that of free water. Viscosity of bound water is greater than that of free water. Surface tension of bound water is lesser than that of free water. So which are the statement or statements that are true, and why? What is the major reason? Any idea?
So the statement one is true, and
Okay.
I mean, two is also true.
Okay. What about 3 and 4? What about 3 and 4? Any idea?
So they are not true in my opinion.
Okay, you are saying 1 and 2. Why is it so? Why? What is the reason for which you are saying option 1 and 2 is right? Please feel free to answer.
So I can't explain further, but just uh, it was discussed in the online class, so that's why I remember. Yes.
So, as you rightly mentioned, boiling point of bound water is greater than that of free water. So, boiling point of free water is 100 degree. It is also not 100 degree. So here major issue is free water, in the sense here it is in the free water is in the force, right? This is in the force. Understood? So now, so if water is without, there is a difference between here free water also mentions gravity water. So it is free from any forces of attraction from the soil grains. So and but uh, that is not the case with bound water. So bound water is at, attracted towards the grain by electrostatic forces. Usually it is hydrogen bonds. So for for converting that bound water into vapor, you need extra energy to be supplied. So that is why it is the boiling point of bound water will be more than, that is, if you consider it 100 degrees centigrade, you need to supply more than 100 degrees centigrade in order to vap yeah, in order to convert bound water to vapor. So this statement is true. And for freezing point is concerned, that is what. So free water freezes at 0 degree centigrade, and bound water, since these attraction are present, you need to supply, you need to remove extra energy. So that results in further dip in freezing point. So that is why freezing point of bound water will be lesser than 0. It will be in minus. That depends on the thickness and what type of it depends on salinity. It depends on the thickness, which indirectly depends on the mineralogy and uh, grain water surface and several other parameters. So this option is also right. So coming to the third option, viscosity of bound water is greater than that of free water. So when this statement is considered, viscosity is defined as uh, as the resistance to flow. So since the bound water is attracted to the grains by electrostatic forces of attraction, so the ease by which the bound water moves will be lesser. So hence bound water's viscosity will be more than that of free water. So that is uh, the statement 3 is also right. Now, the surface tension of bound water is lesser than that of free water. That is not the case because of this attraction forces. The surface tension will be more in case of bound water compared to that of free water. So this statement is wrong. So as far as this question is considered, options statements 1, 2, and 3 are right. Any doubts? Any doubts?
No, sir. Fine.
Please
So
proceed.
here some interesting research is going on. I would like to add this. So now several people are working on freezing characteristics of soils. So in this regard, so it plays a very important role, and uh, so it at any temperatures, uh, what is the amount of ice and what is the amount of water that has not been converted to ice. So that is one of the major research questions which is getting investigated right now, and several techniques are there to establish that. So in this regard, sands is relatively easy, but when it comes to play in the presence of bound water, so it poses a further challenging issue. So you can refer some literature. Actually, right now it struck me. So if I have some literature, I can also share. So it is, as far as undergraduates are considered, you can just know where the broader area of researchers are, and if you are too much interested, you can just search in website about freezing characteristics of sands or soils. So it is one of the most interesting topics of research as far as geotechnical engineering is concerned. So how pore pressure varies, and several other things are being explored now. So I can share the links maybe in the next. I will write it down. I will note it down. So I will share the links in the next class without fail. Thank you for notifying me. All right. So I just thought of. So it was going very in a routine manner. So I thought of giving an idea. So in what aspect research are getting uh, is is proceeding in this regard. So these are some of the aspects of fundamental research which is still being continued. Coming to the next question, which of the following statements are true? Which of the following statements are true? Phreatic line is the boundary between Vadose zone and saturated zone. Water in the Vadose zone will be under tension. Water in the saturated zone will have a high pressure compared to that of phreatic line. All of the above.
Sir, all of the above.
Okay. So now let us go by option by option. So phreatic line is the boundary between Vadose zone and saturated zone. So Vadose zone is essentially a partially saturated zone, and if you take the water profile, it will be partially saturated, and at a particular point it will be completely saturated, which usually we demarcate as groundwater level, generally in a general term. Now above this, up to a certain point, it will be a partially saturated zone, which is known as Vadose zone. This is completely saturated zone, and above that it will be a dry, or sometimes it will be hygroscopic moisture. So uh, but it is considered as a dry zone. So dry, Vadose, and uh, completely saturated zone. Now phreatic line is that it is a zone which differentiates Vadose zone and saturated zone, and the characteristics of this phreatic line is the water at this line exists at atmospheric pressure. All right. So this is the main characteristics of phreatic line. So the pore pressure at the atmosphere phreatic line will be equal to atmospheric pressure. So as far as this is concerned, option A is right. Now water in the Vadose zone will be under tension. So now when you consider grains, let us consider ideal grain where water is present completely. Let us consider a fully saturated zone. What happens is that water will be under a compression and soil grains will be in tension. So that is what usually occurs. But when in a partially saturated system, soil will be in compression and water will be in tension. So that is why since water is in tension, it tends to pull the soil grains together. So it tends to pull the soil grains together. Hence, soil grains will be under compression and water will be in tension. So that is why, since you are exposed to effective stress problems now, so the pore pressure above the groundwater level is negative. So that is the sign convention which we use for compression and tension. So tension we consider it as negative, and compression we consider it as positive as far as soil mechanics is considered, and in that pore pressure is considered, which is slightly different to what you are usually exposed to in strength of materials and solid mechanics, right? So this statement is also right. Now water in the saturated zone will have higher pressure compared to that of phreatic line. So water in saturated zone will have higher pressure. That is, it denotes the pore water pressure, right? So this is pore water pressure. Now pore water pressure is depends on the depth. So ideally gamma W H or Z. So since height increases, that is the depth increases, H will not be a right term. It will be Z. Z will be a more uh, Z is depth. Now as depth increases, pressure is also increasing. So at phreatic line, ideally the depth is 0, for which the entire excess pore water pressure will be 0 plus 0 in the sense it will be at atmospheric conditions. So water in the saturated zone will have higher pressure compared to that of phreatic line. So saturated zone in the sense just below the phreatic line. So option C is also right. So the right option is all of the above. Any confusions or any doubts?
Sir, can I clarify a small doubt, sir?
Yeah, yeah,
Mm, Can you draw in Wadow's zone two grains and water, sir?
yeah. That is
Both you have
possible.
drawn actually in saturation. Can you just try it so that I can clarify it out
Yeah, yeah. So
somewhere?
here two grains will be there,
Okay.
and usually at a partially saturated zone, how to draw exactly is water will be present like this. So it will be a meniscus kind of thing.
Okay, sir.
So that is why water tends to pull the grains together.
Here only I am getting a doubt, sir. Actually,
Yeah,
soil is in water is in tension, soil is in compression.
compression. Yes.
But if the soil is in compression,
Mm-hmm.
why we get a sorry, I confused with the tensile cracks in earth pressure. I'm sorry, sir. No,
Yeah,
it's okay. We are
yeah,
talking about capillary only,
yeah,
right?
yeah. Capillary action only.
Yes, yes, sir. Fine,
So,
sir.
as far as you are concerned, what you have mentioned at the time, soil itself will be in tension due to
Yeah,
the
yeah.
crack formation.
Crack formation. I confused with that and this.
Yeah, yeah.
Otherwise, okay, sir. Fine.
So, moving to the next question. This is ninth question. So, we will solve a numerical on effective stresses. So, a river is 2 meter deep. The river bed consists of saturated sand with a unit weight 20 kilonewton per meter cube. What is the effective stress 4 meter at 4 meter below the top of the sand? So the river is 2 meter deep in the sense first always since some UG undergraduates are there. So the first aspect is that draw a figure of it. So you draw first the ground level. So ground level, that is the river bed, and the water level. Now this is water level, and this is the river, and this is 2 meters, right? Now you have the characteristics of sand and consider gamma W as 10 kilonewton per meter cube, right? Now now the river bed consists of saturated sand of unit weight 20 kilonewton per meter cube. So gamma sat, since it is completely saturated, you need not bother about other densities, other unit weights. It is completely saturated, 20 kilonewton per meter cube. Now you what we need is effective stress at 4 meter. So let us consider a point P. which is at 4 meters. All right. Now, always in the initial practice, when you are newly exposed to this subject, always try to compute in terms of figures. So you draw the profile. So initially, this is the reference. Now at point 0, first we can draw the total stress. Now total stress at this is consider a point A, that is A, B and point P. At A it will be 0, right? Any doubts?
No, sir. Okay.
And at B, at B, point B,
20 kPa.
it will be pressure due to the water column, which is 10 into 2, right? Now at 4 meters. So what happens is that this 20 will continue and further it is 4. So the water pressure will constitute to again sorry. So now it is, since the how to put it, so here it will be 20, it is 2 into 10. Further here it will be due to the saturated uh, saturated unit weight, that is stress is gamma sat into Z, which will give 20 into 4. It is due to the soil that is present, 80. Any doubts till now?
No, sir. Clear.
Okay. So the total will be how much? Total effect, total stress at P will be
100.
100. 80 plus 20. Now coming to the pore water pressure. So this, so at this is gamma W into 4. This is the pore water pressure. This 10 into 4, which is 40 kPa. This is total is 100 kPa.
Sir?
Yeah. So the water column above also, I think
Yeah, we have to start
we
from the
have
top.
to, yeah, we have to start from the top,
Yeah.
which will be 20 plus 40, which will come to 60 kPa.
Yes, sir. Diagram we need to little bit modify.
Yeah, 60 kPa. So always start from above. So just a minute, I will modify it. So it will be 0, will be 20, will be 40 plus 20, it will be 60, right? So now the effective stress is defined as
You
total
can
stress.
erase these two, sir. Sorry, sir. You can erase the 10 into 4 and 40 kb also.
Yeah.
Because later any people refer it is
So now
40 also you can erase, sir.
that is okay. So
Yeah.
there has
Now
been
it
a
now it is
confusion.
fine. Now it is fine.
So that effective stress is defined as total stress minus 4 water pressure, right? Now it will be 100 minus 60, which will give 40 kPa. So here compare putting it as one more easy way of doing it is uh, not an easy way. How to understand it is, so here the stress, that is the pressure you are calculating gamma sat is including that of water's unit weight. So you need not this and this is devoid of porous media, and hence this water pressure also acts on the soil layer beneath it. So that is why in the case of total stress you take this into consideration. All right, so it will be A. So moving to the next question. A layer of compacted clay extends from the ground level up to a depth of 6 meters. A layer of compacted clay, I think this will be question 10. A layer of compacted clay extends from ground level up to a depth of 16 meter and overlies a 6 meter thick sand layer. So let us draw the diagram. So this is ground level, and clay extends from ground level up to a depth of 6 meters and overlays a 6 meter thick sand layer. Now this is, let us consider clay layer, which is 6 meters, and it overlays a sand layer of 6 meters, right? Sand layers of 6 meters, sand layer. Now the thing is, the saturated unit weight of the sand and clay are 19 kilonewton per meter cube and 20 kilonewton per meter cube. And below, before that, a 2-meter thick capillary saturation zone has been identified above the clay sand interface. So now since so and the water table is at 6 meters beneath the ground level. So this is water table, and since the pore size of clay layer is very small, it tends to uh, exhibit a capillary phenomena. So that extends up to 2 meters, where the water has risen and the saturation here is 100%. Saturation is 100% due to capillary rise. So, and the characteristics of the soil is, here it is 16 kilonewton per meter cube, and this is 19, sorry, this is 20 kilonewton per meter cube, and this is 19 kilonewton per meter cube. Till now, any confusions are there? Please let me know.
No, sir.
Okay. So now there are a series of questions. So before that, uh, please give me just a minute. So I'll be back in a minute. So I'll be back in a minute. Please excuse me. So now coming to the first question of this first sub question, effective stress at 3 meter below the ground level. So first is 3 meters below the ground level, which is now it is no, there is no uh, uh, presence of water, so it is straightforward. A, the answer for A is total stress is equal to effective uh, effective stress plus 4 water pressure, or we can write the other way. We need effective stress. So the effective stress is equal to total stress minus 4 water pressure. So here 4 water pressure is 0. So it is equal to the total stress, which is, you know, the uh, so in this unsaturated, in the sense we can ideally assume it as dry. So it is 16 into the depth is 3 meter. So it is 48 kilopascal. All right. So this is option A. See, the question A. All right. Now coming to the, any doubts till the,
Sir, for other questions, can I take a gamma W10 or 9.25?
yeah, 10 is fine.
Okay, sir. Fine.
Now coming to the next question, pour water pressure at 5 meter below the ground level. So now, since we have two type of water columns here, one is completely saturated where the water column is in compression, and capillary zone where the water pressure is in tension. So we have to first, since it is given 5 meter below ground level, so, and initially the question is that uh, uh, 2 meters above the clay sand interface, we till 2 meters above the clay sand interface, we are experiencing capillary action. So the point which they are mentioning, for which we require the computation, is that it falls within the capillary zone. So now when you draw the diagram, so at capillary zone interface, pore pressure will be 0, and further it will be, when it will be like this. So now here pore water pressure will be negative. This is negative, this is positive. The pore water pressure will be computed from this, by assuming this as reference. So what is the pore water pressure is for a capillary zone is that minus gamma W into Hc at a particular point, right? So Hc in the sense at what point we are measuring. So capillary rise, H is capillary rise till that point. So here it is 1 meter, right? So we need total of 5 meters. 6 minus 1 is 5. So minus gamma W, you can take it as 10, and Hc you can take it as 1, which gives minus 10 kilopascal. All right. This is for B. All right. Now coming to the third question. Total stress at 6 meters below the ground level. Total stress at 6 meters below the ground level. So total stress at below the ground level is that you need direct total stress. It will be 16 into 3 plus 20 into 2, right? So it will be 48 plus 40, which will give you 88 kPa. Now if I extend this to effective stress, then the pore pressure will be negative, and the total effective stress in this point, that is at any point, will be greater than the effective stress will be greater than the total stress. So that will there will be a addition in pore pressure due to the tensor. Yeah.
So there was small error.
Yeah.
They asked a question at 6 meter depth, na, sir?
Total stress at 6 meters.
Yeah, above the capillary zone is 4 meter, but you have taken 3.
Okay. Okay. I thought
Small
it is
error.
4, so it will be 64.
Plus 104 will come.
104. Yeah. Thank you.
Welcome, sir.
So that is the total stress at 6 meters. And now pore pressure at 12 meter below the ground level. So for that, this is the point. So here we need not consider what happens in this zone. So our concern starts from the groundwater table. So it will be linear variation, for which it will be gamma W into 6. Yeah. So Am I audible? Hello?
Yes, sir.
Yeah. So here it will be gamma W into 6. It will be 60 at, we are considering at 12 meters. Now effective stress at 12 meter below the ground level. Now you have to compute the entire total stress minus the pore pressure that is acting at this point. Right. Now, where can I write? So now the total stress is equal to 16 into 4 plus 20 into 2. First 6 meters is first 6 meters is covered, plus for the remaining sand layer saturated unit weight is 19 into 6. So how much is the total stress?
Two and eight.
Yeah, it is 218, and pore water pressure at
60.
that depth is 60. Now effective stress is sigma minus u, which is 218 minus 60, which will give us 158 kp. If you take, we have used 10, and if you calculate with 9.81, you will get some decimals for lesser, higher. You will get around 159 point something. So this is 158. So to summarize it, it is 158 kPa. This is 60 kPa. This is 104 kPa. This is minus 10 kPa. This is 48 kPa. Hope it is clear.
Yes, sir.
Okay. Now coming to the next question, it will be question 11 and 12. Well graded sand should have, it may be a multiple correct option. Well graded sand should have uniformity coefficient greater than 4, uniformity coefficient greater than 6, coefficient of curvature between 1 and 3, effective size greater than 1 mm. Well graded sand should have. What would be the answer? So it is straight from Atterberg's limits.
Sir, can I clarify small doubt, sir?
Yeah, yeah.
Is this program is for only our country students or even for abroad also?
No, this is ideally for NPTEL. So, but we will be uploading this video. Actually, what these uh, uh, these videos will be visible, will be uh, given only for the learners who have registered. But however, we are as PMRF scholars, we are mandated to upload this in YouTube.
You know, why I am asking this question is GATE
Yeah,
exam is now other country people also taking.
yeah, yeah,
This is indirectly helpful for the GATE students.
yeah,
For example, in this question, vulgar design means it is as per Indian standard you are asking, right?
yeah, yeah. This is as per Indian standards.
That's why I'm asking, sir. If the
Yeah,
question they are going to read in other country people, they will have a confusion, I think.
yeah, yeah. So this is as per Indian standards. So
Uh,
usually it is as you rightly mentioned. Nowadays there has been a increase in the people who are writing gate from abroad also.
yes, sir.
So, but these questions were framed during the earlier launching of the courses, so they might not have kept this in mind.
Hmm.
So, for the future reference, it has to be kept in mind.
Yes,
So,
sir. Yes, sir. Question has to be little bit framed as per IS code or something you have to write.
or it has to be specified.
Yes, sir. Thank
So,
you.
so for sand, it should be Cu should be greater than 6, and coefficient of curvature should be between 1 and 3. So, B and C are the options. Right? Now, soil having liquid limit and plastic limit values as 40% and 20% respectively, and the proportion of soil passing 75 micron sieve is 50%. Right? Soil having liquid limit and plastic limit values as 40% and 20% respectively, and the proportion of soil passing 75 micron sieve is 50%. Find the group index of the soil. So group index is ideally used uh, in classifying geomaterials for pavement purposes. So I will just write the relation for group index. So group index is mostly an empirical relation. So group index is 0.2a plus 0.005 AC plus 0.01 B into B. So B, C, D are uh, parameters where A is uh, so percentage that is passing 75 microns, and in this case the range of percentage will be from 35 to 75. All right. Now, how will we calculate A is that, so this percentage should be 35 to 75, and first you have to check whether the given percentage is falling. So 50% is falling under this range. Now, in order to get A is obtained by the value you got here, 50 minus 35. So the uh, that is the additional percentage of soil that is passing through 75 micron sieve from 35. So if you take this is an integer which it will be a proper integer value for which its range is from 0 to 40. So now if it is that, if this value is 35%, it will be 0. If it is its value is 40%, it will be 5, like that. So this value is 15. Now similarly for B, the same value is, the range is from 15% to 55%. So B will be 50 minus 15, that will be 35. And C value, for which we need plasticity index, sorry, C will be liquid limit. So liquid limit is 40%. So when its value is ranging from 40 to 60. So it should be liquid limit of the soil minus 40. The range is from 40 to 60. So since it is 40, it will be 0. Hence this parameter entirely will be 0. And D will be for plasticity index. Plasticity index can be calculated by 40 minus 20, which is 20%. So this value ranges from 10 to 30. So it has a numerical value of 20. So we have 20, it is 20 minus 10, which is 10. So now we have the values. A is 15, B is 55, C is 0, D is 10. Now uh, you can substitute these values here. GI will be 0.2 into 15, it will be 3, plus 0.01 into B is 35, D is 10, it will be 350, into 0.01. It will be 35 plus 3, which is group index. So there is a major flaw in this question. What is the flaw here? Any idea? Any idea what is the flaw? Please, if you are aware, you can say.
C is 0, sir. From that you should get some conclusion.
No, actually, the basic, what is the range of group index we have?
That is 0 to 20.
So we are getting higher values. So ideally, we should consider it as 20. So here, the value we are getting is around 38, right?
Where, sir? What is the A first part?
A is
Point 2,
15.
point 2 times A, na?
Yeah, 15, it will be
What is a
3.
point? What is a point 2 times A? A is
15.
15 into 2,
Point 2 is
30.
3.
Point 2, it is a 3 now. 3 plus
3.
3.5.
And this one,
Last
0.0.
third part is 350 into point not 1 is 3.5, no, sir?
350 into Yeah, yeah.
point
Okay,
zero.
okay, 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 okay. There is a calculation mistake. Yeah, yeah,
Yeah, it is a 6.5 final answer.
yeah, yeah. 3.5. So it will be 6.5. Right, right. So and
Okay.
you can eliminate this option, this one, this
Yeah.
it initially itself, since the values range from 1 to 0 to 20. So
Yes, sir.
0 corresponds to very good soil and 20 corresponds to very poor gradings. So that is the ideal understanding. So now we can solve an issue problem. We can solve this problem and come to the later part of these questions. So these are mostly small questions which we can address later. So now, if consider this question: if the groundwater table lowers from 2 meters to 4 meters, what will be the change in effective stress at a point 6 meters below the ground level? Will it increase or decrease from the previous condition? Right? Now, if the groundwater table lowers from 2 meters to 4 meters, what will be the change in effective stress at a point 6 meters below the ground level? So, now let us draw the diagram here. This is ground level, and initially water table is at 2 meters. This is 0. This, let us consider the reference. 2 meters, there is a groundwater table, and this is gamma dry, which is 16 kilonewton per meter cube. All right. Now we need effective stress at point 6 meters. Now this is, let's consider this point 6 meter. 6 meters from ground level. All right. Now first condition is this one. So let us calculate the effective stress for this condition. All right. So first you calculate total stress. So consider gamma W as 10. All right. Total stress will be gamma. This initially it will be gamma dry. This is gamma submerged is 10 kilonewton per meter cube. In order to understand well, you calculate gamma sat. So gamma sat is defined as, or gamma submerged is defined as gamma sat minus gamma W, right? So gamma total stress is 16 into 2 plus 20 into 4, which gives us 80 plus 32, 112 kilo Pascal. Now we need 4 water pressure. 4 water pressure in that condition is 4, gamma W is 10, 10 into 4, which is 40 kilopascal. So sigma dash is 82. Understood? This is for the first case. Now
सर एक्सक्यूज मी सर, ये 20 कैसे आया, ये नहीं समझ में आया।
कौन सा 20?
ये 20 into 4 किया ना आपने।
अच्छा अच्छा, ठीक है। ये क्या होता है ना, हमको दिया है गामा सबमर्ज्ड, राइट? लेकिन ये टोटल स्ट्रेस कैलकुलेट करने के लिए हमको चाहिए सैचुरेटेड यूनिट वेट। सो गामा सैचुरेटेड, that is, as I mentioned, gamma submerged is gamma saturated minus gamma W. I told you to take gamma W as 10. Now you need gamma saturated, for which you can, uh, now if you need gamma sat, you need to add gamma submerged plus gamma W. So 10 plus 10,
ओके।
it will be 20. All right.
Sir, final answer is 72, not 82.
40. Yeah,
One,
yeah, yeah. 40, right? Okay.
yes, sir.
72. 72. Now second case, it is reducing to 4 meters. That is, the dry part is increasing. Now this is 4 meters. Now what happens to total stresses? Earlier it was 16 into 2. Now it is 16 into 4. Ignore the capillary action, plus 20 into 2, which is 64 plus 40, 104 kilopascal. And pore water pressure in this condition is 10 into 2, which is 20 kPa. Right? Now gamma dash is 104 minus 20, which is 84. All right. Now, if you consider what is happening from case 1 to case 2, there is an increase of effective stress. The magnitude is 12, right? So the option is 12 kilonewton per meter square, and it is increase. All right. So this point, so it has several interpretations. Now the effective stress which we are calculating is the stress that is acting at on the soil at that point, right? Now if you consider a real life scenario where you are drawing a well, drawing water, or there is a sudden drop down of water level, that is the most critical condition which we consider for design or anything, or analysis or design, on further design. So why is that? Because the material property is not going to change, uh, but the water table, since it is getting down, there is an increase in the effective stress as you observe here. So since if there is an increase in effective stress, that means the ultimate load acting on the soil from grain to grain contact is increasing. So that will lead to imminent shear failure. So that is why this condition is very critical in uh, flow problems, which we will be discussing in further weeks. All right. So right now, this is one of the important basic observations which you might have to remember. All right. And similarly, one more observation is there, which I will discuss now. So consider this question 18. All right. The water table at a location is at the ground surface and the saturated unit weight of the soil is 20 kilonewton per meter cube. Alright, if due to heavy precipitation, the water level rises to 2 meters above the ground level, the increase in the vertical effective stress at a point 2 meter below the ground surface will be. Now we have to understand the question now. So initial condition is that there is a ground level and at the same level there is a water table. That is what they are saying. And the unit weight of soil, saturated unit weight is 20. Now the point of consideration is 2 meters. Right. So let it be point P. Right. Now this is the first condition. Let us calculate the effective stress. Effective stress is 20 into 2. Let gamma W be 10. 10 into 2, which is 40 minus 20, it is 20 kPa. Right. Now second condition is that the water table, this is the ground level, and water table is increased up to 2 meters, and the soil is already saturated, so it is 20 kilonewton per meter cube. The point is same point, which is at 2 meter from ground level. Now let us calculate the effective stress. Now effective stress will be the pressure due to water above the water table 10 into 2 plus the due to the soil 20 into 2 minus the pore pressure due to the above water column 10 into 2 plus 10 into 2, which is pore water pressure below the ground level. So if you see, this and this get cancelled, and ideally you get 20 kPa. So if you notice the change here, it will be 0. Now this is also one of the important observations. So once the effective stress is independent of the water column above the ground level. That is free water column, not within the uh, uh, within the soil layers. Once it is above the soil layer, the effective stress is independent of the water level. So this is also one of the observation. So if you get a question or if you come across a situation where where somebody put forth that there is a change in water level, what happens to the effective stress, you can straight away say that it will be 0. So you need not consider it as there will be no change in effective stress at all. All right, this is also one of the important observations. So this is option A is the right answer. So coming to this question, uh, the minimum value of group index soil which are the statement are correct. So the minimum value of group index soil is 0 and the maximum value of group index for soil is 20. So as I discussed before, both the options are right. Now coming to the next question, the plasticity of clay is due to. Plasticity of the clay is due to mainly its adsorbed water. So capillary water is contributes to the negative pore water pressure. Water will be in tension. Gravitational water and free water is analogous. So the uh, main aspect governing the plasticity of the clay is adsorbed water, which indirectly governs the plasticity index. Any doubts? I think it is straightforward questions. So some questions are directly straightforward. So that's why I'm going pretty quickly.
Sir,
Yeah.
sorry for interrupting.
No, no, sure, sure.
Uh, Free water, also called as a gravity water, and also it is a is it? It's also called pore water. Pore water.
Yeah, yeah. Actually, pore water in the sense, usually we address pore water as free water only.
Okay.
So
Now my question is,
yeah,
how do you find adsorbed water in percentage? I think I have not seen anywhere in books about how to calculate the adsorbed water.
it is a very good question. Actually, there are several techniques for which you can calculate the. You cannot calculate percentage of adsorbed water. You can calculate the thickness of the layer, double layer.
Okay.
So that can be done by several properties
Adva-
like zeta potential, and
uh-huh.
there are various electrical techniques for which and several models are there for by which you can determine the thickness of adsorbed water.
Okay. What is that, sir? You use about zeta potential.
Yeah, zeta potential.
Okay. Can I search Google afterwards?
Yeah, yeah, you can search.
Okay, sir. Go ahead, sir. Done, sir.
Yeah. So and coming to the next question, as per the IS classification, Indian standards, the expression for A line is. So this is a there is no concept behind this. This is a thing that you need to remember. So the theoretical value for the A line is plasticity index is equal to 0.73 liquid limit minus 20. So this is the line. When you calculate if your plasticity index is measured plasticity index is above this value, you classify it as clay, and if it is below this, you classify it as silts. So that is the basic classification, and further from liquid limits, you classify what is the plasticity of the clay, whether it is low plastic, medium plastic, or high plastic. So this is option C. All right. Coming to the next question. As per the IS soil classification system, a soil sample of a silty clay with liquid limit of 40% and plasticity index of 20%. All right. So liquid limit of 40%, then it falls under intermediate plasticity. You can straight away say. Now you need to calculate the theoretical IP, which is 0.73 into WL minus 20. So this is 0.73 into 40 minus 20. So how much it will be? It will be, I think it will be lesser than 20 obviously. So the 20 point lies above the A line. So which is clay. So it is classified as intermediate clay with intermediate plasticity. All right. And fine grained soil is surrounded by a thin layer of water, which is known as bound water. And in some cases, when the soil is completely air dried, there will be some water present that will be known as hygroscopic water. So that cannot be removed when you air dry it. You have to dry it completely in oven for 24 hours at 100 degrees centigrade. And if you again place the soil in the atmospheric condition, it will absorb some water, which is known that also is termed as hygroscopic water. Right. So that is one additional information.
Sir, first one also called bound water, also called adsorbed water, no, sir?
This is adsorbed. This
Okay.
is option B is absorbed.
Yes, sir. I saw it. I saw it.
Yeah. So
And another small clarification is
yeah.
option A is property of the grain. Is it right, sir?
Yeah, exactly.
And option D is actually soil matrix.
Yeah,
Is it right, sir?
right.
Okay, sir. Fine.
Uh, so that is entire soil. Uh, that it is the nature of the soil as a matrix itself. So bound water is that it is also a bulk property, but it is major role is played by the single grain. See, even for sands, you have some hygroscopic moisture content, which will be very less. And clay also, you have some hygroscopic moisture content. You cannot neglect that. So that is dependent on all the atmospheric factors and humidity conditions and several other factors. So, but bound water is purely the electrostatic force of attraction that is acting between the soil grains and water. All right. So with this, we will be concluding this session. Hope this session was useful. So this session will be online on every Saturdays 5 p.m. to 7 p.m. I encourage all the learners to join the session and uh, get benefited. So and by several questions which you raise, so it is a mutual learning. So
Sir, one thing I want to say,
yeah,
if this time can be altered to some other time, like 6 to 8.
no, that
If
cannot be
other,
done because let me
okay,
say.
yeah,
So usually what happens is that we are already given the time slot from NPTEL office, that is from IIT Madras.
okay,
So that cannot be changed. So it will be, it is a very lengthy process and people may not approve also. So usually we are strictly advised to stick to this timing. So
okay,
even if we are not available, so that also is not encouraged. So uh, so that is why uh, we are mandated to make us available in this time frame.
okay, sir, no issue. Yeah,
Okay. So
thank you.
thank you for attending. Hope we will meet in the next week and some. I am looking forward for good discussions. Thank you.
Thank you, sir.